So connectivity or vertex connectivity is kappa, denoted by kappa. So what is vertex cut or separating set? It's basically a set of vertices whose deletion creates more than one component or the graph has a single vertex. Okay. And what is connectivity or vertex connectivity? The minimum number of vertices whose deletion creates more than one component or the graph has a single vertex. Actually, this definition was come in the exam. Now, if the connectivity of a graph is kappa, if somebody tells you if vertex connectivity or connectivity of a graph is kappa, the immediate thing that should come into your mind that division of kappa minus 1 vertices can't make it disconnected. Okay, so ये बहुत important बात है. So if somebody say it is a k connected graph, so it means that deletion of k minus 1 vertices cannot disconnect the graph. Okay, so in other words, k connected graph का एक definition आप ये भी दे सकते हो कि it is a graph whose vertex connectivity is at least k. क्योंकि अगर exactly k होगा तभी k minus 1 vertex remove करोगे तो ग्राफ डिस्कनेक्ट नहीं होगा. अगर इसका ओरिजिनल कनेक्टिविटी k plus 1 भी है, in that case also k minus 1 vertices delete करोगे तो it won't be disconnected. So k connected graph is deletion of k minus 1 vertices cannot disconnect the graph. Okay. So here are so for suppose for this graph. Okay. So this red vertex. So these three vertices actually, if we delete them, it disconnects the graph. Now, if you delete these two also, it also disconnects the graph. So if I talk about the connectivity of this graph, its connectivity is actually 2. It is a 2 connected graph. Actually, no, sorry, it's not a 2 connected, it's a 1 connected graph, because if you delete this, then it creates this component. So it is a 1 connected graph. So suppose this is a 2 connected graph. You have to delete these two to make it disconnected. If it is a complete graph, then this definition comes: the minimum number of vertices whose deletion creates a graph having a single vertex. So यहाँ पे 3 vertex delete करने के बाद ही एक single vertex मिलेंगे. So connectivity of complete graph Kn is basically n minus 1. So at least from this definition, from all this definition, few things are clear to us. So amongst the important part is vertex connectivity is a number. It is just a number, and that number signifies that minimum number of vertices whose deletion create more than one component or the graph has a single vertex. If it is a k connected graph, then it meaning its connectivity है at least k, and that means deletion of k minus 1 vertices cannot disconnect the graph. Okay, you choose any k minus 1 vertices out of it, but it can't disconnect the graph. And for a complete graph, it is basically, if it is kn, its connectivity is n minus 1. Now, equivalent connectivity, which is totally defined based on vertex. So edge connectivity, so edge से कुछ भी टर्म होगा तो प्राइम आ जाता है. So it is kappa prime. So ये notations are very important. जैसे हम लोगों ने अल्फा, बीटा, अल्फा प्राइम, बीटा प्राइम ये सब चीज पढ़े थे. So like when we are talking about maximum independent set, so it is alpha. The size of the maximum independent set, that is denoted by alpha. Then what was alpha prime? So it is prime, that is edge. So size of the maximum matching, is alpha prime. Similarly, beta g is minimum vertex cover, and beta prime g is minimum edge cover. Similarly, kappa is vertex connectivity, kappa prime g is edge connectivity. So there are two things. One thing is called disconnecting set. Disconnecting set says that a set of edges whose deletion creates more than one component. जैसे इस ग्राफ अगर देखो, यहाँ पे all these red edges are actually create the disconnecting. So if you delete them, it creates three components. Okay, so this is a disconnecting set. Okay, then this red one and this all this blue one, sorry, all this yellow one. If you delete them also, it creates more than one component. And what is edge connectivity? The edge connectivity is the minimum number of edges whose deletion creates more than one component. So that is denoted by kappa prime. And k edge connected graph is again deletion of k minus 1 edges cannot disconnect the graph. Now disconnecting के set के साथ मतलब don't confuse it with edge cut. Disconnecting set says that a set of edges whose deletion creates more than one component. Now what is edge cut? Edge cut is the set of edges between which creates two components, S and V minus S. So यहाँ पे बोल रहा है कि a set of edges whose deletion creates more than one component. It may be 3, it may be 4, anything. But for edge cut, it must be 2. A set of edges whose deletion creates exactly two components. Say for example here in this graph, these 3 edges consist of an edge cut, or these 2 edges consist of an edge cut. But if you take all these 5 edges, it is not an edge cut because it creates 3 components. And here the minimum edge cut size is 2. So the edge connectivity of this graph is 2. Because if I delete these 2 edges, it will disconnect the graph. So the set of edges between S and V minus S. V is all the set of vertices and it is V minus S. So S is a subset of V. Now what is edge cut? And edge cut is nothing but a minimal disconnecting set. It is not the minimum disconnecting set. Just say if I delete these 3, it is an edge cut. It is a minimal disconnecting set. Why? Because from this, if I add one more edge, again it connects the graph. Okay, so it is a minimum number of edges that is disconnecting them. Not a minimal set of edges that disconnect the graph. But it is not the minimum edge cut. Minimum edge cut is this 2. So minimum edge cut is definitely a minimal disconnecting set, but the vice versa is not true. So it is not that if it is a minimal disconnecting set, then it will be an edge cut, but it may not be the minimum edge cut. Okay. So edge cut का जो notation है ऐसे S and V minus S, where V is the set of vertices in the graph. So S is a set of vertex, V minus S. So it will create basically 2 components. So edge cut means all the edges that are across this part, right? S to V minus S. It may so happen there are edges across S, there are edges within V minus S. That is possible. Okay. But when I am saying this, so it actually denotes the set of edges whose one endpoint is in S and the other one is in V minus S. Now some special graphs. So complete graph के लिए हम लोग जानते हैं कि इसका edge connectivity and vertex connectivity दोनों ही है n-1. Okay. Then complete bipartite graph KMN. जैसे ये इसके लिए it will be minimum of m and n, so it will be 1 in that case. So if I delete this vertex, it will disconnect the graph. Similarly, if I delete it, so that is why the vertex connectivity is 1. And if I say delete this edge, then also it is disconnected, because there is a single vertex here, there are two vertices here. So minimum edge cut or edge connectivity is also minimum of M and N, where M and N are the size of the partites. M is the number of vertices in some partite and N is the number of vertices in other partite. So for hypercube, Qn is vertex connectivity and edge connectivity, both are N. Okay, and but we have to prove it. We have to prove this claim. And for three regular graph, it says that for any three regular graph, if its vertex connectivity is x, then its edge connectivity must be x. So vertex connectivity equal to edge connectivity for any three regular graph. So ये last जो statement है, that we need to prove. So we'll prove that the vertex connectivity or connectivity of Qk is k. That is something we need to prove. And to prove that, the procedure here is, first we'll prove connectivity of Qk is less than equal to k, and then we'll prove the connectivity of Qk is greater than equal to k. And both of these satisfy parallelly, simultaneously. In that case, we say that it is indeed k. So first I will prove that the connectivity of Qk is k. So first of all, if k equal to 0, Q0 means there is a single vertex. So that is a complete graph of one vertices. And we know that for a complete graph, the connectivity is, for kn, the connectivity is n minus 1. So k1 ke liye it will be 0. Okay. So Q0 ke liye connectivity is 0. So for Q0 it is proved. For Q1, basically it is nothing but an edge, but this is also K2. So K2 is a complete graph of two vertices and its connectivity will be 2 minus 1, that is 1. So Q1 के लिए 1 and Q0 के लिए 0 आ रहा है. So for Q0 and QR we have proven the fact. Okay. For Q2, which has two square vertices, 4 vertices, Q3 to Q8 vertices and Qn2 to the n vertices, हर एक vertex के जो neighbors हैं, they create, the neighbors of a vertex creates a vertex cut. जैसे इसका neighbor है these two red vertices, so they create a vertex cut. इस vertex का neighbor है these three red vertices, so they create a vertex cut. So definitely the connectivity of Qk is at most k. इतने तो होंगे ही. So that is why it can be trivially proved that for Qk where k greater than equal to 2, the neighbors of the vertex actually creates the vertex cut. So we can say that the connectivity of Qk must be less than equal to k. That is the number of neighbors for a particular vertex. The top part is you have to prove that connectivity of Qk is greater than equal to k. Okay, so we do it here. So our task is to prove connectivity of Qk is greater than equal to k. We know that Q0 is not equal to K1. So by definition, its connectivity has 0. So Q0 ki connectivity has 0, Q1 ki connectivity has 1, and that is coming from the definition of connectivity. From the definition of connectivity, we can prove this. So for Q0, Q1, it is trivially proved. Now, induction hypothesis says that the claim connectivity of Qk minus 1 is greater than equal to k minus 1 is true for all I. So less than equal to k minus 1. So I should say so. So the claimed continuity of qi minus 1 is greater than equal to I minus 1. This is true for all I. Uh, so I should write qi. So the claim is qi greater than equal to I. That is true for all I less than equal to k minus 1. Okay, and we have to prove this claim from qk. Okay, so to prove it, so how qk is being composed of? Qk is composed of, we have two qk minus 1 and qk minus 1. And for all set of vertices here, so it has 2 to the k minus 1 vertices. It also has 2 to the of k minus 1 vertices, and we for each of the vertex pair we have an edge. So here there are 2 to the k minus 1 edges. Okay, and that is how we create qk. All right. So to prove it for qk, connectivity of qk greater than equal to k. So suppose S is a vertex cut of qk. Suppose S is a vertex cut for qk, and we also assume that S is neither a vertex cut for q prime and q double prime. Q prime is this uh, hypercube whose order is k minus 1, and q double prime is this hypercube whose order is also k minus 1. Okay, so S, we say that suppose S is a vertex cut for qk, but it is neither a vertex cut for q prime and q double prime. What does that mean? If S is a vertex cut for qk, but it is not a vertex cut of q prime and q double prime, it means that that vertex cut consists of every vertex so S contains at least one vertex from each matched pair of q prime and q. So it may be this, I can choose this vertex, I can choose this vertex, and I can choose this vertex. Then it creates an vertex. Then it creates a vertex cut. Where, okay, so in that case, mod S will be greater than equal to 2 to the k minus 1. So if S, so basically what I am trying to say, if S is a vertex cut of qk and S is not a vertex cut of q prime and q double prime, which are essentially qk minus 1, it is the meaning है कि mod S, the size of mod S will be 2 to the k minus 1, because there are 2 to the k minus 1 matched edges across it. So we have to choose one vertex from each of the edges to create the vertex as S. But we already have proven that mod S less than equal to k. That is already we have proven. So if mod S less than equal to k, mod S cannot be greater than equal to 2 to the k minus 1. So इसका मीनिंग ये है कि S is a vertex cut of qk, but it also acts as a vertex cut for at least q prime or q double prime. So here we say that, so here mod S greater than, but we know that mod S less than equal to k. So it is a contradiction. since it is a contradiction, so what we have supposed is wrong. So contradiction means यहाँ पे AC is the vertex cut of QK, and our assumption was this. The AC is the vertex cut of QK, but it is not it is neither a vertex cut of Q prime and Q double prime. And we proved that it is, from here we come to a contradiction. So that means our assumption is wrong. So what is the knot of it? What is the knot of this assumption? That means either Q prime or Q double prime will be disconnected if AC is a vertex cut of QK. So at least one of Q prime and Q double prime is also disconnected when AC is a vertex cut of QK. Now, at least one of Q prime and Q double prime is disconnected. Suppose Q prime is only disconnected. Without loss of generality is considered, suppose Q prime is only disconnected. From induction hypothesis, since Q prime is basically QK minus 1, so इसका connectivity है K minus 1 equal to K minus 1, that we have got from this. So since Q prime is only disconnected, so vertex cut S has at least K minus 1 vertices. So vertex cut S has at least K minus 1 vertices from Q prime. So because S is a vertex cut for QK and S is also a vertex cut for Q prime. From induction hypothesis we know that Q prime को disconnect करने के लिए exactly K minus 1 vertices लगेंगे. So S is a vertex cut for QK. So vertex cut में at least K minus 1 vertices तो रहेंगे and that must be from Q prime. Okay. Now, if vertex cut S doesn't have any vertex from Q double prime, if vertex cut S does not have any vertex from Q double prime, then we say that QK is connected. Okay, to tell this statement, to understand the statement, we draw a picture. So let's take it. So sorry. Okay. Okay, so basically, so Q3 is composed of two Q2s, right? So Q3 is composed of two Q2s. Now what it says, okay, if you go by this statement, so Q3 के लिए मैं बता रहा हूं कि so suppose AC is a vertex cut for Q3, AC is a vertex cut for Q3, and we have said that it also acts as a vertex cut for this q prime. So this is q prime and this is my q double prime. So if I q prime and this is my q double prime. Suppose S is a vertex cut of Q3 and it is also as a vertex cut as of this Q prime. Now Q prime Q2 के from induction hypothesis we have proven that इसका vertex cut है equal to 2. So S must have at least 2 vertices from Q prime. Now it says that suppose S doesn't have any vertices from this Q double prime. So what we have told here, S is a vertex cut for Q3. Also, suppose S is a vertex cut for Q prime, which is nothing but equal to Q2. Now, since connectivity of Q prime equal to 2 that we have got from induction hypothesis, we can say that S has at least 2 vertices from Q prime. Now suppose, now assumption is S doesn't contain any vertex from Q double prime. S does not contain any vertex from Q double prime. Now that is not possible. Why? If it doesn't contain any vertex of, then if we delete these two, then what happens? Just look into this picture. Then if we delete these two, अगर मैं इसको delete कर दूं, तो ये सब एजेस डिलीट हो जाएंगे. अगर मैं इसको भी डिलीट कर दूं, तो ये डिलीट हो जाए. बट इट इज अ कनेक्टेड ग्राफ, but it remains connected after deletion of these two. So that means S does not contain any vertex from Q prime. But in that case, what happens? It implies that S cannot be a vertex cut it implies that S cannot be a vertex cut for QK. That means S has at least one vertex from Q double prime. And what does that mean? That means that mod S is greater than equal to 2 vertex from this Q2 plus at least one vertex, 2 vertex from Q prime and at least one vertex from Q double prime. So basically it is 3. So that is the logic that is being put over here. If vertex cut S has at least k minus vertex from Q prime. So if vertex cut S does not have any vertex from Q double prime, then QK is actually connected. Why it is connected? That is being written here. So it implies that Q double prime has at least one vertex in the vertex cut S. So mod S का size होगा this k minus 1 plus 1 k. So at least greater than equal to k. We already have proven that mod S less than equal to k. हम लोग यहाँ पे प्रूफ किए थे कि connectivity is less than equal to k. और यहाँ पे हम लोगों ने vertex cut का size जो है we have proved that it is greater than equal to k. So taking both into consideration, the connectivity of QK is actually equal to k. Okay, so that is how we prove it. Now we prove some we will prove that chi prime g less than equal to delta g. What is chi prime g? Chi prime g is basically our H connectivity, and delta g is minimum degree of the graph. Minimum degree of a vertex in the graph. Now that is very obvious because if some vertex has minimum degree, जैसे इस ग्राफ में इस vertex का डिग्री सबसे कम है, इसके इंसिडेंट जो भी vertex होंगे, इसके इंसिडेंट जो edges होंगे, if I delete them, then it basically disconnects the graph. So the edges incident to a vertex V of minimum degree form an H cut. So definitely chi prime G must be less than or equal to delta G. Okay, so that is a very straightforward proof. Now we will prove that chi G less than equal to chi prime G. That is, vertex connectivity is always less than equal to H connectivity. This is a very interesting proof, and this proof actually gives you an algorithm also. So we will see how this will come. So consider. So basically here we have, so this is a H connectivity. Suppose consider a minimum H cut S V minus S. Okay, that means this is the minimum number of, so across S V minus S, there are the minimum number of edges there for the graph. If we delete them, it will create this H cut S and V minus S. Now our objective is to find a vertex cut whose size is less than equal to this minimum H cut. If we are able to do that, then we are done. Case 1 is, it is an easier case. Every vertex of S is adjacent to every vertex of V minus S. Every vertex of S is adjacent to every vertex of V minus S. In that case, what will be the size of this cut? Mod S into V minus S. So what is the size of this cut? So there are 2, there are 4. So 2 into 4. 8 edges will be there. Right? So K prime G will be mod S into V minus S. Now, what is the minimum value of this possible? The minimum of it is reached when either mod S or mod V minus S is 1. That is the possibility. So it must be greater than equal to V minus 1. So try to understand this thing. So first we consider a minimum H cut is V minus S, and our objective is to find a vertex cut whose size is less than equal to this. Now case 1 is, suppose every vertex of S is adjacent to every vertex of V minus S. Then how many edges are there across this H cut? It is mod S into mod V minus S. Now what is the minimum value of it? The minimum will be reached when any one of them is 1. So if any one of them is 1, the other must be V minus 1. Other must be V minus 1, because that is the definition of H cut. It will create only 2 components of the graph. So it must surely be mod V minus 1. Now we know that from the definition of vertex connectivity, that the maximum value of a vertex connectivity can be mod v minus 1 for any graph, and which is basically true for complete graph. For complete graph, kn, its vertex connectivity is actually n minus 1. So we can say that for the from the definition of connectivity or vertex connectivity, we know that this mod p minus 1 is the upper bound for connectivity of a graph. So we have proven that chi prime g is greater than equal to v minus 1, and v minus 1 again greater than equal to kg. So chi prime g greater than equal to chi g. So this is the easier case to prove. A bit involved case is, suppose every vertex of S is adjacent to every, so there is at least one vertex in S which is not adjacent to some vertex in V minus S. That is the not part. So what will be the case 2? Case 2 will be it's not. So every vertex of S is adjacent to every vertex of V minus S. So it should be like there is at least one vertex X of S which is not adjacent to some vertex Y in V minus S. Okay. So case 2 is there is at least one vertex X belongs to S which is not adjacent to Y which is in V minus S. Okay. Now our objective is to find any vertex card whose size is less than equal to this S V minus S. So our objective is, suppose we have a minimum edge cut, and it is not a edge cut where every vertex in S is adjacent to every vertex in V minus S. So it is a different kind of min cut, minimum edge cut, where at least there is some vertex X which is not adjacent to Y, which is in the other part at V minus S. Okay, now our objective is to find some vertex cut whose size is less than equal to this minimum edge cut. Now since it is any vertex cut, so that must be इसके जो connectivity होंगे, that must be greater than chi g. So this is my chi prime g. From chi prime g, I am creating some vertex cut whose size is less than or equal to this. And since it is a sum vertex cut, it must be greater than equal to the minimum vertex cut. That is why chi g less than equal to chi prime g. So our objective here is to create some vertex cut whose size is less than S, V minus S का जो size होगा उससे. So our objective is to find a vertex cut whose size is at most the size of this edge cut, minimum edge cut. How do we do that? So suppose this is X and this is Y and they are not adjacent. Then what I will do, X के जितने भी vertex adjacent vertex हैं which are in V minus S, मैं उन vertex को T से denote कर रहा हूँ. So X के ये दो vertex है adjacent which are in V minus S. So I will mark them as T. Okay. Also, in partite S, I will mark all those vertices as T which has at least one neighbor in V minus S. Okay, so say for example, so P is a vertex cut whose size is less than equal to A. So T मैं क्या करूँगा? A union B, where A is taken from V minus S and B, the set of vertices B, will taken from S. So what is A? A is the set of vertices in V minus S which are adjacent to X. So these two vertices belong to A. And what is B? B is the set of vertices in S minus X. तो X के अलावा जितने भी vertex हैं, amongst them, the set of vertices in S minus X which are adjacent to some vertex in V minus S. Okay, जैसे if there is some edge within this, then none of them vertices belong to B, because okay, so set of vertices in S minus X which is adjacent to some vertex in V minus S. So this and this, none of them are adjacent to any vertex here. So they don't belong to me. But why this is T? Because they are adjacent to some vertex from here. Even we will consider this vertex also. So this vertex is adjacent to some vertex here. This vertex is also adjacent to some vertex here. This vertex is also adjacent to some vertex here. Now, what happened? Now this T acts as a vertex cut for X and Y, right? Because अगर तुम X and Y को separate करना चाहते हो, so if you so this T is basically A union B. So set of vertices from here and set of vertices from here. Now this T acts as a vertex cut from X and Y because there is a path from X to Y through these vertices. Okay. Now this we say that the size of this number of vertices in T must be less than equal to S comma V minus S. Why? Because for each vertex in T, we can select a distinct edge from S comma V minus S. जैसे इस टी के लिए मैं इस एज को चूज करूंगा, इस टी के लिए मैं इस एज को चूज करूंगा. दे आर डिस्टिंक्ट एजेस एंड दे बिलोंग टू दिस एस v minus s. Then this vertex is adjacent to some vertex here. तो मैं इस एज को भी मैं रेट कर सकता था, इस एज को भी मैं रेट कर सकता था. But among these three edges I choose any one of them. Similarly for here also, this t is adjacent to this y, so I choose this edge and I choose this edge. So mod t का size always less than equal to s v minus s होगा, because for each, so all these edges creates this edge cut, minimum edge cut. Now for each vertex in T, we can select a distinct edge from s comma v minus s. So it gives basically an algorithm to find a set of vertices that acts as a xy separator. Okay, so if you delete these vertices from this graph, definitely x and y will be separated. Okay, now we create T as a vertex cut, and it is a vertex cut, and definitely this vertex cut must be greater than equal to minimum vertex cut. So size of this minimum vertex cut will be chi g. So chi g less than equal to mod T, which is less than equal to again s v minus s, mod s v minus s, which is minimum edge cut. So chi g less than equal to chi prime g. Okay, so if we take both of them, so we see that chi g less than equal to chi prime g less than equal to delta g. So taking this chi g for any graph g, chi prime g equal to less than delta g and chi g less than equal to chi prime g. So taken both of them, we can write that for any graph g, chi g less than equal to k prime g less than equal to delta g. Okay. So you can take a break for 5 minutes and then we will again start. So these are the things we have proven. So after 5 minutes, I will again start. Okay, so the next thing we'll prove that if it is a three regular graph, then it is a vertex connectivity equal to edge connectivity. Now we know that for any graph, vertex connectivity is less than equal to edge connectivity. So it is also true for the three regular graph. Now what we can do, given a minimum vertex cut of the graph, we construct an edge cut of the same size. If we do that, we are done. Given a minimum vertex cut of this, if we construct an edge cut of the same size, then we can say that both are equal. Now you look into this picture. So suppose this is the whole graph G, and you have a minimum vertex cut S of G. So this S is a minimum vertex cut. So it contains a few vertices. It contains the set of vertices, minimum set of vertices. If we remove them, the graph will be disconnected. Now, since it is a three regular graph, okay, so since it is a three regular graph, then every vertex has three neighbors. So every vertex in S has three neighbors. Now suppose W is a vertex in the vertex cut. So what are the status of its neighbors? So one neighbor must be in H1, one neighbor must be in H2, and the third neighbor may be in H1, may be in H2. Okay, so if it is in H1, it is like this. If it is in H2, the case is like this. If X for the vertex X. So both edges are there and the third edge is there. And there is a third option. The third edge is amongst the vertex cut itself. Okay, so these are the three options possible. For a given vertex, one edge must be here and other edge must be here. So that is true for W, X, Y, and Z. The thing is for the third vertex. The third vertex may be in H1, the third vertex may be in H2, and the third vertex may be in S itself, which is again itself is a cut vertex. Okay. So there is a common edge between them. Now, so what is the size of this vertex cut? Its size is 4. Now I have to create an edge cut of size 4. So what I will do, if both edges are in H1, then I will take the other edge. I took this edge for this vertex. For X, I will take this edge which is going to H1 because two other edges are in H2. For this kind of cases, I will, for Y and Z, I will take two edges on the same side. Suppose I take it for H1 side. Okay. Then I create a edge cut of size 4. So this edge, every vertex in S has one neighbor in H1 and the other neighbor in H2. Okay, now I can create an edge cut of like this. So this is a red edge, this belongs to the edge cut, this belongs to the edge cut, and these two red edges are in the edge cut. So this size is also 4. So, and we are done. Okay, so that is why for a three regular graph, chi g equal to chi prime g. Next, we will prove a theorem. If S is a set of vertices in G, then S V minus S, this edge cut with a complex, very complex equation. Okay, that is summation of degree of vertices in S minus 2 into. So what is GS? GS is a subgraph of G which is induced by S. Okay, so it says all. So GS means the subgraph induced by G for S. So how do we prove it? So here S V minus is an edge cut and GS is a subgraph of G induced by S, and we have to prove this. So We have to prove this one. Basically, if we have to prove this, that means we have to prove that the summation of degree of all the vertices in S, summation in all the vertices in S is basically this one plus 2 into EGS. Now we have to look that the status of the vertices in S. Sorry. So we have to take the what are the edges. So if S is a set of vertices in G, that means all other vertices belongs to V minus S. So there are some edges which are across S and V minus S. Consider the edges S and V minus S. Now for all these edges, this contributes to degree 1 to the vertices in S. So इस edge के लिए इस vertex के लिए 1 degree add होगा, इस edge के लिए भी 1 degree add होगा. So all the vertices which are across S, V minus S, each edge contributes 1 to this value. And if the edge is for GS, which is a subgraph of G induced by S, so all the edges within it, every edge contributes 2 to the degree. So each edge contributes 2 to this term. So from this we can easily say that summation of this is 1 into S V minus S, because each edge contributes 1, and here each edge contributes 2 into EGS. Then this is the direct result. Okay. The next theorem is if G is a simple graph, and for this H cut S V minus H is less than delta G for some non-empty proper subset S of G. So for some proper subset S of the vertices, if the size of the H cut is less than equal to delta G, strictly less than delta G, then mod S, the size of and the number of vertices in S must be greater than delta G. Okay. So how do we prove it? We will prove the earlier theorem. Okay, we will use this as our starting point. So given is S comma V minus S is delta G. So what is S V minus S? It is this formula is we got from the last proof, that mod S comma V minus S is basically equal to, if you look into this, delta dV, where V belongs to S is the summation, minus 2 EGS. Okay. Now what we can tell about this one? This is a summation of degree of all the vertices in S. So delta G is the minimum degree of the graph, and mod S is the number of vertices here. So mod S into delta G, mod S is the number of vertices in S, and if I multiply everything with delta G is the minimum degree of the graph. So this number must be less than equal to this, because यहाँ पे भी all of the vertices in S is considered, and definitely dV must be greater than equal to delta G for all the vertices. So this relation holds. And what we can talk about EGS, number of edges in GS. So it has mod S vertices, so maximum edges would be, since it is a simple graph, it will be S into S minus 1 by 2, right? So I take this by 2 on this side, so I can write that minus S into S minus 1 is less than equal to minus 2 into EGS. Okay. Now I add these two, this one and this one. So what I will get? So summation of dV minus 2 EGS is basically delta G. So this line we have got from the earlier theorem. Now, instead of this, I can write it S into dg, and instead of this minus 2 EGS, we can write that it is minus S into S minus 1. Okay, we replace this value. Okay, so this value is replaced here, and this value is replaced here. Then simple mathematics. So this will come to this side and this will go to the other side. Okay, so what happens? That S into S minus 1, it goes to the other side, that is greater than equal to delta G into S minus 1. Okay. Now S minus 1 cancels out from both sides, so mod is greater than delta G. So so with this I end today's class, and so in the next class we will cover this part, and from next Friday onwards we will discuss only algorithms. Okay, or it may so happen in the next class I will discuss one algorithm on. Hello. So the thing is, in the next class maybe I will discuss any algorithm, and maybe the next class I will prove few theorems. Then again I will continue with the algorithm. Let's see what I can do. So for today itself, this is the thing, because it's too much theorems, so I don't want to go into a lot of them. So thank you.
Thank you, sir.